All right, I think it's a good time to get started. Thank you all for joining us from around the world. Just a reminder, this is the second day of our SOFIA school. We had a talk this morning that was rescheduled for March 7th, James Randomski's talk. Our first talk this morning is going to be Chick Woodward from the University of Minnesota, and he's going to be talking about the forecast Grism Spectroscopy in a star's environment, dust mineralogy. So, Chick, go
Well,
ahead.
thank you, Steve. Yesterday, we heard a number of very interesting and exciting talks where people described how they approached and utilized SOFIA data sets for a wide variety of applications. And I'm going to continue along that line, talking about things that we do with forecast as part of a team effort to study certain types of stellar environments. And as usual, we have the usual distractions in the background and they will disappear in a while. So um, thanks for taking the time to come in and chat with me. What I'm going to be describing basically is a program that's developed out of a long-standing international collaboration to study transient phenomenon in the galactic sky. And we heard yesterday about the utility of forecast as being a facility that can respond relatively rapidly to new events in a wavelength region where a lot of diagnostic sorts of measurements can be made. And in particularly, I'm going to be focusing on dust studies. The 3 to 35 micron region of the electromagnetic spectrum is very rich in signatures that can tell us the composition of refractory species that often are found or condensed in circumstellar environments. And understanding this pathway from the creation of these refractory species to their incorporation in protoplanetary disks to their eventually accretion into planetesimals really is kind of a narrative arc of our origins. It helps us understand how we build rocky planets. In addition, studying emission features in this wavelength gives us some insight into types of organic species that are present in these environments and allow us to study this pathway of organic delivery. Now, I've been on a team for a while, and you heard Margaret describe her evolution in infrared astronomy. This international team that I've been working with has had a long history of studying explosive events in the night sky for a number of interesting reasons. One is the philosophy that these things are really exciting sorts of outbursts to study, and if you can use the infrared, you can understand a lot about how potentially dust condenses in these environments as part of a larger story, a panchromatic story that allows you to understand the evolution and activity of these events across the electromagnetic spectrum. So today I'm going to be focusing on some work that we've been doing with SOFIA, not only studying explosive events, but in particular a very famous, interesting event um, which is the V838 Monocerotis event. Now, V838 Monocerotis is an example of what we would call a luminous red variable that's characterized by very high luminosities, very low effective temperatures, and long time scales for evolution after they erupt. And this is actually rather interesting because it gives you a window of many tens to hundreds of days to follow the evolution of these particular systems. And probably all of you have seen the very famous HST image of V838 Monocerotis. You see that in the background, and superimposed upon that, you see some results of a forecast study of these types of objects. Now, it's rather interesting because we also heard a very nice talk about the Ursa archive. One of the things that one likes to do when you're studying these transient events is to go back in various archives and try to understand whether there have been previous observations that can give you some insight into what you may or may not find in your observations that are conducted in the current epoch. Now, V838 Mon was certainly well studied. It's one of the best studied luminous red variables, and we know a lot about what was happening shortly after its eruption. There was a very famous light echo that was studied that allowed us to pin the distance down to the source. And since that time, both spectroscopic observations at near infrared wavelengths and optical wavelengths have revealed a lot of new information about how that source evolved. You couple that with recent ALMA studies, and you begin to get a very interesting picture about the cause potentially of some of these events. Initially, the nature of red luminous variables was essentially not well understood. There was a number of different theories that suggested their possible origins, ranging from nova-like eruptions, which is accretion of hydrogen-rich material onto the surface of a white dwarf that would lead to an explosion. There was other scenarios that suggested these objects were ingesting their planetary systems, swallowing them, or maybe they were like HEB stars that had very late thermal pulses. But I think it's becoming pretty clear that objects like V838 Mon in our own galaxy, their origin lies in stellar mergers. And so understanding the local universe archetype allows us to extend our understanding out to other galaxies where telescopes like James Webb Space Telescope will be making a lot of headway. So what I'm showing you here is a composite from the Spitzer data taken in 2008, that's indicated in the red, and superimposed upon that is the SOFIA data that was obtained in 2019. And again, the SOFIA data is markedly different than what was observed in one of the earlier Spitzer epochs. And this actually started off part of a long investigative series about what the SOFIA data is trying to tell us, how we analyze the SOFIA data, and what we were actually observing. So again, as Lisa pointed out yesterday, the URSA archive is a great repository to go data mining and find things that are extremely useful in enabling you interpretation of objects. So part of this program that we conducted with SOFIA was designed not only to get low resolution spectroscopy across the wavelength range that forecast operates, which is about 5 to 30 microns, but also to obtain imagery. And we heard from Emma's talk yesterday about the importance of getting imagery photometry points in order to fill in the spectral energy distribution. Well, we've found the most advantageous way to use forecast combines both imagery and spectroscopy for a number of reasons that I'm going to discuss. So keep this figure in mind. Now, part of the thing that we have come to understand in interpreting SOFIA data is because the Grism segments are not contiguous or overlapping, it's often useful to get a measure from a photometric filter that one can use to assess the calibration of each independent Grism segment coming out of the pipeline. Now, over 10 cycles, the calibration algorithms for the forecast instrument have markedly improved. But again, it's interesting to compare the photometric imagery with the Grism flux levels. And as we saw yesterday, you can obtain the filter transmission profiles and convolve that with the Grism spectra, and then do aperture photometry on forecast imagery to look at the range of the overall photometric error and to understand whether that's within the cal error and statistical error that one would anticipate. And what I'm going to be describing is sort of a multi-phase approach to analyzing the spectroscopic data. Understanding the information that's contained in the spectrum relies on trying to disentangle the information that the emitting species in the infrared are conveying through the electromagnetic spectrum. And imagery is important to this because it provides a way to do aperture photometry on your source, to provide the broadband photometric measurements for the spectral energy distributions, allows you to assess the Grism stitching. That's kind of important for a source like ours that can vary or other objects that we study that have a more rapidly varying time scale. So if you get successive observations of a particular target, you want to assess the overall changes in the spectral energy distribution and their level. That's also very useful for the point spread function determination when you're looking for extended structure. So I'm showing you two examples of forecast imagery. Often we use the 19.7 micron filter to do peak up observations in order to center the source in the slit. And I'm showing you another representative image at 11.2 microns. Now, we heard yesterday that there's a wide variety of applicable tools and techniques out there to do your photometry. One of the approaches that we've taken, if the tool is already written, let's try to figure out how to use it to our advantage. And we found using the aperture photometry tool is a very quick way through a graphical user interface to do the aperture photometry. And so I suggest one, check out this particular tool. It's an IDL-based tool. When you get the images out of the URSA database, there are multiple planes in there. There's the flux plane, there's the variance plane, there's the coverage plane, and all of these can be used to build up the photometry values that you would use in the interpretation of the spectrum. Now, one of the other things to note is that the orientation of the forecast Grism slit on an object is fairly arbitrary because the slit is actually rotating on the sky, and they have to derotate the slit every 15 minutes or so. So in some sense, what you're doing is getting an integrated picture of the particular object as the slit is rotating over the target. The other thing to note, and probably will be the conversation in the March uh, presentation, there's a number of different artifacts in the forecast data that one has to be aware of. In particular, using some of the narrowband filters, you do get some ghost images that appear, and in particular in the 11.2 micron filter, I point out where one of the ghosts is. Now, the objective behind this process is to combine the photometry with the low resolution Grism observations to do spectral energy decomposition. And I'm going to talk about at least one technique that our group has used multiple times in the past, and it's kind of an interesting way to approach disentangling the spectral energy distribution to learn about the refractory species that are contributing to this observed spectral energy distribution. Now, I might point out that one of the things that puzzled our group for a long time was actually what was going on in this region of the electromagnetic spectrum. You can see that there's some very deep features in this particular region of the forecast G111 Grism. And that led us to a lot of forensic conversation. And I encourage you, as the observer, to enter into dialogues with your support scientist in the SSC when you don't quite understand what the data products are delivered to you are telling you, and also to understand whether or not the data should be reprocessed. Now, we were a bit startled, I must say, initially when we got this data, because unlike any other data sets that we'd actually observed. So we did spend some time going back and forth, trying to understand what the pipeline process was that led to the release data. And I'd also point out that the SSC has now actually released their pipelines to the community as a Python-based tool product. And so you could do some of this on your own and modify the reduction algorithms to suit your particular needs. But at the time that these data were obtained, the way to interact with the data products and assess their the fidelity of the pipeline was to have a conversation with the support scientist. So what you see here are two panels. One is this region in the forecast Grism 1111 setting. The blue dots are the spectrum of the target. The red dotted dots are the model atmospheric transmission. And you can see the transmission runs from 0 to 1 over here. And what we also retrieved from the database after some conversation is the spectral energy distribution in the same grading for the calibration star that was observed on this particular flight series. One of the things that we did is we talked to a number of the investigators on this particular flight series and asked, do you see any sorts of odd data artifacts? Because initially this was very hard for us to interpret. The other thing that one has to do is, given that there are still some regions of deep telluric absorption, even at flight altitudes of 43,000 feet where these data were obtained, one has to try to understand whether some of the features that you see that are deep inside these telluric absorption features can be trusted, and attempt to draw some cut as to which data you would include in your model. After numerous conversations, we decided to apply a cut at about 65 to 70% transmission. So some of these data points in here were not used in the analysis. You can see in alpha set, which is a much brighter target, there's a lot of scatter in the data still, but there's not this large spike that we don't quite understand. And perhaps in some sources that have similar emission characteristics, there are real features here, but given the nature of the depth of the absorption and the sharpness of this feature, it possibly could be an artifact of the data processing. Now, in the infrared region of the electromagnetic spectrum, it's been well known that a number of different refractory species have these prominent emission features in here. And this is just an example taken from the work of Koika et al. That shows you from 7 to 30 microns or so that there's numerous bumps and wiggles in the spectrum of astronomically significant sorts of refractory species. So these are an example of magnesium-rich silicon oxides here of different magnesium to silicate ratio running from phosphorite all the way up to a pure end member phayolite. And this is an example of the type of information that one can get if one does spectral energy decomposition, assuming a particular refractory mineral composition. Now, the models that we were going to use had to find optical constants for the type of representative astronomical refractory species that we thought might represent the emitting components in V838 Monocerotis. There's a very useful database of these optical constants that exists at Heidelberg Jena. And if you're ever interested in getting optical constants for a wide variety of materials, from silicates all the way down to various ices, you can actually download these particular optical constants and use them in your radiative transfer models. And indeed, that's what we did. In order to analyze the forecast spectrum, to try to understand what the emitting components are, we did use radiative transfer modeling. We heard a number of talks yesterday that invoke different sorts of radiative transfer codes that are out there. I just highlight a few here that are commonly used. We heard about Dusty yesterday. We actually used a version of Dusty that had a component in it that turned on a circumstellar disk. That's Dusty 4. There's Mod, there's Hyperion, there's the Skirt project, which gives you three-dimensional ray tracing, radiative transfer. There's codes like Dustum. Basically, all of these particular codes require some understanding or some modeling of the grain size distribution that is present in these circumstellar environments, the grain composition, and perhaps secondary components of emission that exist that might be stellar or otherwise, and some conversation about the optical depth. Now, what we did is ran a series of model grids looking at a number of different variables using this Dusty disk model. And so I just point out 4 panels here. And often in the analysis of the spectral energy distribution, even at low resolution from Grism data, it takes a lot of work. So several thousands of models were actually generated to provide model grids that allowed us to try to ascertain which might be the best composite model that would fit the data. So I'm showing here examples of various Dusty outputs here where we vary the optical depth towards the source, looking at the structure for particular sorts of species. This particular environment is oxygen rich. Early observations showed the presence of gas phase aluminum oxides and silicon oxides and the presence of H2S emission. So initially we canted our models towards those sorts of species. So we can see in this panel here that we ran for fixed ratios in the grain distribution of silicon to aluminum over a range of optical depths. And you can see how the spectral energy distribution of the model would change. And then for fixed optical depths, we of course ran a suite of models that varied the distribution in terms of the grain composition from one that was dominated by silicate sorts of species and no alumina to one that's all 100% aluminum. And that also showed you a change in the emergent spectral energy distribution. And the idea here is to take the best model, perhaps add another composite emission feature in here to represent a secondary component to replicate the observed Grism data. So running through that process, which takes several months to find a best fit model, on the left-hand side, you can see the SOFIA Grism data here, the different segments, and then a number of different models. One of the other things that was quite important in this particular study, and I encourage folks to do it, is to get ancillary data. So these black dots here represent photometry, both at optical and infrared wavelengths that have been de-reddened and used to help constrain the spectral energy distribution out of the models. And eventually, you can develop a best fit model. And that's shown in this particular panel over here, where the black dots again represent the de-reddened photometry at short wavelengths. The orange boxes here actually are quite important. These orange boxes allow us to pin the spectral energy distribution at very long wavelengths here. And you can see how they fall over the Grism data out at this wavelength. And so eventually, through modeling, and looking at our grid of models, we were able to develop this composite green spectrum here that's a reasonable fit to the data and allow us to try to assess whether we're looking at a condensation sequence that theoretically had been predicted to occur in oxygen-rich environments as the temperature of the material changes. One of the other things I would like to encourage folks to do is that when you have a very interesting result in your data analysis is to reach out to the SOFIA Science Center folks and tell them, hey, I've got something that is an interesting scientific discovery that might create a lot of buzz, and so they will go off and they will think about it and work with you to develop a little release on this. For this particular object, there's a little NASA blog that was created. The other thing that's very useful, if you're asked to join the AAS Journals chat, if you happen to publish in that journal, sometimes you might be asked to give an author YouTube chat under an interview. That also occurred for this particular paper. And it's a good way to promote the science that you do, but also, more importantly, to promote the capabilities of a facility that allow you to get some extremely interesting data. I'd like to also thank my teammates that were involved on this. Like many science projects today, it's an international effort, drawing in the expertise of a number of investigators to help you understand the data and do the scientific interpretation. And so I think for the folks in the audience that enjoy working with teams, SOFIA provides a very interesting environment to do this, and we're looking forward to future studies of these sorts of targets in the future. And so with that, I would like to conclude. If there are any questions or comments, I can take a few verbally now. I will be monitoring the Slack channel later in the day. Unfortunately, I have to dash to go teach a couple of classes shortly, but thank you very much for your attention, and I'll take any questions you might have.
Thanks, Chick. So we have one question already in Slack. The dip in the spectrum near 11 to 13 microns is due to pipeline artifacts, or is it an actual astrophysical phenomenon?
So I think they were referring to this dip right here. Could you repeat the question, Steve? I'm sorry.
Yeah, it's near 11 to 13 micrometers.
Yeah, 11 to 13. Yeah, so this dip in here, um, in certain AGB stars, that dip has been putatively um, attributed to certain types of mineral species in those particular objects. We cannot replicate that precisely. Certainly, the region in this region right here is often associated with silicate sorts of material being in absorption. Those are the well-known features in oxygen-rich environments that are associated with the 9.7 micron absorption feature. That's attributed to silicon monoxide. But the origin of this, and in particular this sharp spike and downturn here, there is a sharp spinel resonance feature over here. But I think what this is perhaps suggesting to us, because the spectral energies distribution repeated itself on two independent flights, there was nothing pathological seen in the same Grism spectrum of other observers on that particular flight leg. This is a real puzzle. And whether or not that phenomenon is related to some astrophysical dust species that we haven't quite identified, or a pipeline artifact, is still one of these deep mysteries that we're trying to understand.
All right, thanks. I got some more questions. Could you say a bit more about the PSF determination that you pointed out?
Oh, the PSF determination. Yes, the PSF determination, what we were looking at is for extended emission. Higher resolution ALMA observations actually show a very, very complex structure associated with one of the B stars that fall within the aperture of the Grism data. And so even though forecast imagery has a PSF of the order of a few arcseconds, depending upon which filter you have. The question that we were asking, given the depth of our images, is there any very low surface brightness emission that might be associated with this ridge of emission that's seen in ALMA data? And that's why we're looking at what the PSF distribution was, to get some understanding of where the noise floor was in our data.
Great. We got another one that was, what is the grain size distribution that you used for the dusty modeling of V88,
Right.
V838 Mon?
Right. As you can see, that is one of the parameters that we did look at. We adopted a standard Mathis MRN grain size distribution where, the grain size distribution goes as Q to the power of alpha. We chose alpha to be 3.5. Again, what the actual grain size distribution is in a particular circumstellar environment is often a subject of debate. There are many different power law distributions that are used. And so we thought to first order that the MRN grain size distribution was a reasonable adaptation. It is certainly one of the axes of parameter space that one can investigate, but we got some satisfactory results using the MNR distribution.
Okay, we have another question from Eric Becklin. Go ahead, Eric.
Yeah, nice talk, Chick. A couple of questions. I think you answered one of them, but there is extended emission. Is some of the variation between Spitzer at the shorter wavelengths in SOFIA, could that be an aperture effect? And have you
Yes.
carefully calibrated that?
We, yeah, so you're talking about this particular,
the very first one.
this one here, yeah.
Yeah.
Yeah, we did look into the aperture effect issue. One of the other unfortunate circumstances is there is shorter wavelength Spitzer data in this region here. However, it's saturated. About 80% of the pixels are saturated. There is another Spitzer spectrum that was pulled from the archive that was taken a little bit earlier than the one that's presented here. And that particular spectrum just comes up like this and rolls over to here. And so this dip here was in the second Spitzer spectrum, not the first one. So the whole spectral energy distribution in this particular region is evolving, whereas at the longer wavelengths, it seems to be fairly stable over tens of years. So some of this emission must be arising from either a secondary component that could be extended, but what's really going on in this region of the electromagnetic spectrum remains to be seen. And this gets back to another point that Margaret made. SOFIA is very good at studying some of the brighter targets in the universe. At this particular time, this wavelength range, it's bright. Webb has real trouble working in this area right now. So we either have to wait a few years before such that the infrared brightness of the target decreases so we can look at it with Webb, or in the interregnum continue to study objects like this in the local universe with SOFIA to really understand what's happening in this very interesting narrative of real-time grain evolution in a source over human timescales.